We're given a positive sequence series. Every member of the series is non-negative, and the sum of infinite sum is convergent. It's less than positive infinity. I denote it in this way because I can treat this infinite series as a sequence, because every member is non-negative, so therefore the whole sequence is monotonically increasing. Therefore, since it's convergent, that means it is bounded above. So I can denote it in this way. If that's the case, we want to show that also this infinite series from 1 to infinity of square root of an over n is also convergent. So here's first method. Method 1. So I can say that I can treat this as a geometric mean. So geometric mean is no larger than the arithmetic mean. So in other words, the general term square root of an over n is in fact square root of an times 1 over n squared. Right? So what's the arithmetic mean? Right? So the arithmetic mean of those two members. Right? So we have half of this plus that. And this inequality is always true for any value of n, for any positive integer n. So, in other words, we can just say, let's look at the finite sum. So let's just say square root of a1 over 1 plus square root of a2 over 2 plus all the way up to square root of an over n. And this is no larger than half of a1 plus 1 over 1 plus half of a2 plus 1 over 2 square plus all the way up to half of an plus 1 over n squared. All right. So we can just say this is further, this can be written as half of a1 plus a2 all the way up to an plus half of 1 over 1 square plus 1 over 2 square plus all the way up to 1 over n square. So first of all, we're given this infinite sum of an is convergent. In other words, it's bounded above. All right. So since this infinite series is bounded above, how about the finite series? Of course it's bounded above, because it's monotonically increasing, right? And this upper bound has nothing to do with the value of n or whatever, right? So it's a fixed constant. Let's just say the whole thing is no larger than half times some positive constant, m, m1. So represent the upper bound of this. And plus half of, also the general term is n1 over n squared, right? As long as the power is bigger than 1, then we're good, always convergent. Right? So meaning this infinite series where every general term is positive is also bounded above, right, since it's convergent. Maybe bounded above by some positive constant m2. That has nothing to do with n. So this half of m1 plus m2 may be denoted as capital M that's bigger than 0. Right? So finally, we have this finite sum that's bounded above, and this upper bound has nothing to do with value of n. Right. So things we can treat this is a sequence, monotonically increasing sequence. Right. And this monotonically increasing sequence is bounded above. And that upper bound has nothing to do with value of n. So even if n approaches infinity, right, the infinite sum, still bounded above. Right. So meaning really, this is really convergent. Method 2. We can use Cauchy-Schwarz inequality. Right, still we're going to look at the finite sum. So square root of a1 over 1 plus square root of a2 over 2 plus all the way up to square root of an over n. Right? So this is no larger than, so this is a product of square root of a1 times 1 over 1. So square root of a2 times 1 over 2. So I can just square each member. Square each member. So square a1. Square root of a1 squared becomes a1 plus a2 all the way up to an. In the end, we'll take a square root. Because otherwise, if there was a square, we wouldn't have take square root. Since there's no square, so we take square root. Cauchy inequality. Right? So we're going to square each member of 1 over 1, 1 over 2, 1 over 3. Square each of them. Right, so 1 over 1 square plus 1 over 2 square plus all the way up to 1 over n squared. Right, so this is basically the same idea. It looks very similar. So again, our desired finite sum is no larger than this. And like I said, for the same reason, this amount, this sequence, is actually bounded above. Like I said, it's given to be convergent. Right? So of course, it is bounded above, right? So is this. So bounded above, right? Positive constant times positive constant. Take the square root, still a positive constant. Has nothing to do with the value of n. Right? So still this is bounded above.